This lesson takes place in the field of distributed computing and especially fault tolerance. And I will talk about the notion of self-stabilization. So this notion was introduced by Dijkstra in 1974. So to get the intuition, I will first present a very basic example drawn from physics, which is damped pendulum. So imagine that you have a pendulum, initially in this position, in the stable position. Then, for a finite period of time, the pendulum is perturbed. So, for example, someone could shake the pendulum or the wind could blow on the pendulum. We don't care about the details of how it is perturbed. We just know that right after the perturbation, the pendulum will be in an arbitrary position. But thanks to the damping effect, you know that after a finite period of time, the pendulum will return to the stable position. So we will see how this analogy helps to understand the notion of self-stabilization in the context of distributed system. So what is a distributed system? Usually you have a set of processors, P1 to Pn, connected with some communication channels. Each processor has a state. For example, the state could be the values of the variables in the memory of the processor, or the values of the register in the processor Pi. And a configuration is simply the sequence of the vector of states of every processor in the system. Usually, when you design a distributed system, you have legitimate configurations, that is, configurations that are correct relatively to the specification of your task. And also, usually this set of legitimate configurations is stable. That is, if you start from a legitimate configuration and if you can reach another configuration, then this new configuration is also legitimate. However, your distributed system is a physical system, so it may be prone to several kinds of faults. Particularly, there can be transient faults. This is a kind of perturbation of the system for a finite period of time. And this leads to an arbitrary configuration. So the system reaches an arbitrary configuration which is likely not to be legitimate. So now let me explain what is actually a self-stabilizing system. So usually your system starts from a legitimate configuration at the beginning. Then for a finite period of time you have perturbation, transient fault. Thus, at the end of this perturbation, your system has reached an arbitrary configuration in some set of configurations that are likely to be larger than the set of legitimate configurations. Saying that your system is self-stabilizing means that if there are no more perturbations, then after a finite period of time, you will reach the legitimate configurations and stay in the legitimate configurations. So this property of starting from an arbitrary configuration and converging to a legitimate configuration and staying in the legitimate configurations, so this property is called self-stabilization. Now, there is a very important point here to note that perturbation here is not specified. We don't care about how this perturbation occurs. We don't care about the details of the perturbation. For example, we do not care if a bit in the memory was flipped because of a cosmic photon or because of someone in the room. We just assume that after the perturbation, the system has reached an arbitrary configuration. And self-stabilization ensures that after any transient fault, the system will eventually converge to legitimate configuration and stay in the legitimate configurations.